Gotta figure out how close to the mic I can be here. It's been a couple of years since I've done in-person speaking to a large group of people, so it's a pleasure to see everybody in person and to have such a good attendance here today. So, like Chris mentioned, my name is Geoffrey Leeds. I'm the Flex Product Manager here at Insulectro. And today we're just going to go over some of the general overcoming design flex challenges that we seem to get on a day-to-day and sometimes hourly basis. So just a quick show of hands here, how many people have actually designed a flexible PCB before? And of those people who have designed a Flex PCB, how many of you have not designed a PCB or a Flex PCB that have been tasked with trying to design a rigid Flex PCB? Now that's interesting because most people are trying to design rigid Flex these days. So I appreciate the interaction, thank you everybody. But because of that sample size, where only about 6 of you in this room raised your hands for a Flex PCB and the other 50 of you didn't, what we're seeing more and more every single day are designers trying to get into Flex design and they have no idea where to start. And the purpose of this presentation is going to just essentially kind of go over those basics. Yes, Chris?
Who would like to learn more about Flex design?
There we go. That's the real answer. Great question. Thank you. So we're going to talk about just a couple simple things here today. First is just understanding what the building blocks are. Since a lot of you are rigid designers, I've tried to go ahead and correlate the two together so you can, in your mind, frame them up. Go over some of those pitfalls during design and layout, understand the differences between dynamic and static implications and design constraints, and then last but not least, just cover some of the specialty materials. I won't take 40 minutes on it. We'll go very quickly, but it's just something worth mentioning. Got some feedback here. Try not to touch it. All right, here we go. So, in the Flex world, we actually have quite a bit of different material sets that we can utilize in order to build a Flex PCB. This is just a sample of what we have available. And if you're trying to jump into the pond for the first time, this can be quite overwhelming. And the reality is that the building blocks we have are actually very simple and easy to understand. And in order to understand where those materials are used, like everything, we have to consider, well, from step one is what are we trying to design and what are we trying to build? In the Flex world, we have 2 generalized camps. We have a pure Flex design as well as a rigid Flex design where we're trying to make Flex into rigid PCB fabrication technology. So with that said though, we use essentially the same materials in both of those different camps and categories, but we use them in very different ways. Instead of thinking of pre-preg, right, we want to use something called bond ply, which is what we're going to use in between opposing copper planes. Instead of having cores, we have the same core, but it's just a flexible copper clad core, right? And then instead of using solder mask on the outside of your panels once you're finished, we use cover lay to then protect the exterior surface of our circuits to ensure we don't short everything out. And then up here you can see a picture of what a Flex copper core looks like. This is a SEM scan, but what you're looking at is a homogeneous material or polyimide that is in between or laminated between 2 pieces of copper. The benefits here are inherent in the fact that the flexible substrate is flexible, but that it also prevents shorting between the 2 copper planes because it's a homogeneous continuous film. In the rigid world, you can see my highly detailed Microsoft Paint picture, but sometimes these glass weaves can break, puncture, and cause calf failures. So Flex circuits have that inherent nature of being puncture resistant and also calf resistant associated with them. But the general building blocks are instead of solder mask, cover lay, instead of pre-preg, bond ply, and then when we need to use a little bit extra sheet adhesive, it's essentially like adding a little bit more pre-preg to the mix. There's 4 standard types of Flex PCBs as defined by IPC, type 1, 2, 3, and 4. Type 1, 2, and 3 are very similar in the sense of how we process and manufacture them. Type 4 is where the fun is, and if you've been into a PCB board shop before or are a fabricator, you know what kind of fun we can have. It's a very different fabrication process compared to standard PCB processing and standard Flex processing. Type 4 is the #1 most requested design type today, and it's the fastest growing market segment that we're seeing around. Type 1 is just a single-sided Flex circuit, Type 2 is double-sided, Type 3 is multi-layer Flex, and Type 4 is rigid. So it's all pretty straightforward and simple on the surface, but there are some very major differences between these materials when we really start getting into the weeds. To give you an idea of how these materials perform from an electrical standpoint, this is just a graph showing you the bulk dielectric characteristics. Kapton HN is DuPont standard polyimide film. AP is their all polyimide flexible copper clad circuit, and you can see that with a DK of 3.2 and a DF of 0035. Well, in this case, it's 0.02 to 0.003. If you understand the test method, you can understand why those numbers change a little bit. Frequencies change over ranges, or dielectric values change over frequency sweeps. You can see that the CTE of these materials are very similar to that of copper, so very beneficial when used the right way, but when we start using acrylics, we have a little bit of a different problem. But the general idea here is that flexible copper-clad laminates have very good electrical characteristics, and we can either utilize them in the right way, or we can throw them out to lunch depending upon what material sets we then design them with. But before we get there, let's just go over some of those design pitfalls, because from an electrical standpoint, we're generally not putting too high of gigabits through our transmission lines and our microstrips with Flex, and that comes down to the acrylic adhesives. So that is what I'm going to focus on here, and that's just going to be going over what are some of the different design characteristics we need to consider when laying out Flex. So first and foremost is what you can see on the right-hand side here is what we consider a weak design. And what's weak about it is when you look at where's the laser pointer here, you can see that we're not filleting where the trace essentially becomes tangent to the pad itself. If we do not fillet those edges, what's going to happen is we get stress concentration factors at those edges, and that can cause crack initiation. And then the other half of it is, from a fabricator standpoint, we want a little bit of tolerance, so in case our drill moves during the drill file, we're not puncturing that connection, and again, creating an unreliable connector. And then on the left-hand side, you can see if we have like a connector of some kind, we can lay those out differently, but again, the fillet's going to be very important for us to have to increase reliability of the product. On the bottom there is something called rabbit ears. I don't see it a lot, but it's there from time to time. It's kind of an artifact of days bygone, but it is some things that people do is they'll essentially increase the surface area of the pad, so when you're going through any kind of heavy bend or load, you're not going to have a delamination event from the copper to the base material. All polyimide flexible materials that are 4204/11 generally don't have these issues, so you don't need ears to them, but again, it's an artifact. Keep out areas. So what does this mean? In a rigid flex design, we don't want to run our cover lay or our cover coat or the acrylic adhesives into the rigid sections of the board. And there's a number of valid reasons for it, but the biggest one is that acrylic adhesives, when they reach their T/G of 40C, expand significantly. Most epoxy resin systems or rigid resin systems are anywhere between 160 to 260 degrees centigrade before they even hit that T/G moment. But what this means is during the fabrication process, as well as during our solder floating and final validation, the acrylic adhesive can expand and cause problems. By pulling in the fabrication process those acrylic adhesives outside of the rigid section.
Why don't you tell them the problem the acrylic is?
Which problem?
When the acrylic expands in the Z, what does it do to the barrel?
So it'll stress the barrel.
It'll
right?
break it.
Yeah. It'll not just stress it, but it'll break it. You have other issues in chemical processing where it can get some crazy etch back if you don't account for it properly. It causes plating folds. The list can go on and on and on. But to Jerry's point, when you have acrylic in the rigid section, again, you go through a thermal expansion event, that acrylic starts to expand significantly faster and earlier than everything else inside of that package. So that is the biggest reason and driver why we do not want acrylic adhesives inside of the rigid board itself. When we have a little transition zone between two rigid panels, we want to pull that cover lay out or the acrylic adhesives outside of the rigid sections. And we want to make sure we keep the drilled PTHs and other electromechanical structures away because, again, those acrylic adhesives expand and can put undue stress onto our structures and cause early failures. This is one of the largest design flaws that I see with individuals starting to lay out rigid flex or flex designs their first time. It's something that you want to avoid. We also have a little bit different of an issue on the processing side with something called a cover coat adhesive squeeze out. So our cover lay material is a piece of polyimide with the acrylic adhesive co-extruded beneath the bottom side of it. When we open up our pad sizes and then laminate it to the surface instead of using solder mask, it can squeeze out during the lamination process and potentially, as you can see here, squeeze out onto our pad surface. And that can cause all kinds of issues in assembly. We might not have a good connection between the two, and we have different products to help, one, control that resin squeeze out, but our distance between the opening and the pad size is also different per IPC. Chris?
There's a common name for when we cut back the adhesive and the cover coat. It's called bikini construction, just in case someone's not familiar with that term.
It's a very, very utilized term and kind of antiquated, but yes, bikini style fabrication. I like the term selective pullback, but then again, I'm a millennial, so we'll skip over the conversation there. I'm sure guys do. When we look at layout in the flex area itself, we want to make sure that we are doing something different. Normally, like we've talked about earlier, you want to have a strong coupling to ground between your signal and ground plane. But when you're flexing and you're bending that circuit, what can happen is that circuit is now going under a lot of different stresses. You've got compressive stress on the inside edge of that flex, as well as a tensile stress on the outer edge. We want to minimize that stress as much as possible because stress can cause all kinds of problems. Cracks, breaks, failures, electrical issues. You can sometimes cold flow the adhesives, which changes your distance to ground. It's a nightmare. So what you want to do, and what is ideal sometimes, is do an I-beam. Now, some astute electrical engineers out there might point out, well, this can cause crosstalk and other kinds of issues, but again, we are not moving at high enough speeds traditionally to see those kinds of issues. Jerry just gave me an eye because he's like, not anymore. We have tricks of the trade up our sleeve, but again, for most designers getting into flex, it's the basics you want to master before you get into the really intense designs. Make sure when you're routing your signals across a flexible zone that you do not bend them and you do not shift them in any way. What can happen here is, again, here's your flex zone, and you can see we're changing those conductors to line up with a different, let's say, where we have to put our connector. We want to put that in the rigid section. If we put it in the flex section, one, we're going to be going, our bend direction might not be transverse to the grain direction of the copper, and we'll get into copper's impacts here in a minute. But what can happen is that, again, you're putting undue stress onto the flex cable. And when you don't have that assumption that you're bending with the grain direction of the copper, or in some cases with, I don't know, I'm trying to watch the time here too. It's been an hour and a half of lecturing for the guys here today, so we'll keep going. But again, keep it out of the flex zone. You want to make sure it's in the rigid side. So what impacts do the copper grain have on flex design? So if anyone's taken material science class before, you know that when we have RA copper, we're actually taking those copper grains and we're squishing them and we're aligning them in one direction. We can take advantage of that in the flex world. One, not only from a signal integrity standpoint, but primarily from preventing crack initiation from occurring early on. By squeezing those grain boundaries out over one each other, we prevent cracks from being able to penetrate through the copper initially, as well as slowing crack propagation growth. When you get down to thinner flexes for dynamic designs, the equations change a little bit, and we'll get into it, but typically you're going to want to use an RA foil, and you're going to want to route your traces with the grain direction, so that when you bend at 90 degrees or transverse to that grain, you're giving this flex cable the best chance of success it has. There is one thing that I am going to mention and harp on a couple times here. It's keep PTHs out of your flex zones. What we have here is your design file, and you can see that someone has put these stitches in along the outer edge of the flex cable. You should only do this if there's a strong EMI reason for it, meaning there's a lot of energy outside of the signals you want to keep out of your transmissions, or you have a lot of energy inside and you're trying to essentially create a waveguide. As you can see here, these waveguides don't really give us justice, and they're not close enough to our signal carrying transmission lines. This is what the flex cable will look like once fabricated, and then here's when I get the call and I'm on premises and we're trying to look at why these flex cables look like little pouches that have puffed up and now we're failing at final. You want to keep them out of the flex zone. It's not good for bending, because when you bend the PTH, you're going to do this, and you can see the nice little crack that went straight up the edge. And there's other problems to get to something like this. You can let processing chemistry inside the cable. It creates puffers and leakers. There's all kinds of processing problems, but ahead of time, you want to make sure you keep those drilled PTHs outside of your flex zones. And again here, this was a new designer designing their first flex board. There's you can see the PTHs they did drill. And some of them, it's a little bit too close to our keep out areas. The other thing that we can look at is if we have to bend a flex cable beyond what we normally would consider, we can put stress reliefs in them, and we can drill and cut slots in our flex cables that, again, where we know there's going to be stress concentration factors, we can cut it out and eliminate a lot of the stress that may be undue applied to our flex cable. So hopefully you guys all mastered that information and you're now flex experts for design layout. Now we're going to get into just some of the nuance between static and dynamic bending. So static bending is one time, often referred to as bend to install. And the other side we can use flex circuits for is something called dynamic flex or cyclical bending, where it's bending multiple times. Knowing what you're doing ahead of time will prevent a lot of problems, not only from the fabricator side of this, but also from your end of life and considering how this product will perform once it's in the field. Typically for dynamic and for flex in general, you're going to want to go with thinner is better. So the thinner you can make that flex cable, the better it's going to, one, perform from a bending standpoint, but also two, from a performance standpoint. In the bottom left-hand side here, you can see a nice little finite element analysis, courtesy of Flex Design Guidelines. It's above. I was trying to get the ISBN here to give proper credit. I promise there's no plagiarism here. And what they're showing is where we bend this material, you can see the difference between the compressive and tensile strength, and that manifests in the way the material bends. If we bond those flex cables together in something we would consider a book or a bonded flex cable, multiple layers, and we're not doing what's called a bookbinder system, you can see that that tensile strength can actually cause the copper foil to snap on the outer edge. And then on the inside of it, you can see a buckling. So how do we solve some of our electrical issues? Maybe we need to have a certain amount of energy going through those flex cables. Maybe we are at such a high transmission rate, our flex cable, we can't make it, our traces as thin as we want. Thin the trace out, make it a little bit wider. And that does two things. One, it gives you a wider surface area. So if we all remember what stress is, it's force over area. We get a larger cross-sectional area of the copper cable, which means we have less stress being applied to the copper, and hence we won't get to its yield strength or before too long, hopefully. But then it also can help us because we can get a tighter coupling to ground and we can actually get better signal integrity. Things to consider, your bend radius is directly correlated to the thickness of the flex cable. So for a single-sided flex cable, your rough guidelines are your bend radius should be 6 times the overall thickness. So if you have a thickness of 12 mils, your minimum bend radius you can bend this flex cable to before you might see problems is about 72 mils. For multi-layer boards, because it's thicker, right, we can't put as much stress onto it because we're going to change these stress singularities and how they affect our design. We have a different bending rule for them. In this case, it's 12x the thickness of the cross-sectional thickness of the cable. So if we have a 30 mil thick flex window, it would be 360 mils. The one thing that is often missed is surface preparation during fabrication and how that affects not just our flex performance, but our signal integrity on the rigid side. We remove copper at multiple steps during the fab process. We do it when we first pull the panels out of the box, when they start going through interlayer pre-clean. By the time we get to alternative oxide, we can have etched off quite a bit of copper from these traces. What that does is it creates, hopefully you can see it down here, on an RA foil, which is more resilient to etching, it can start to create these deep grooves. These grooves act like little starting cracks. And what can happen in a dynamic event is cracks will start to form and initiate at those points faster than they will at the surface, again, because we have less cross-sectional area at those locations. So we get a larger stress singularity, and then we start seeing cracks and failures before when we thought we would. So it's very important to talk to your fabricators and know which fabricators have understand and profiled this process, so we're starting out with the best foot forward. Up here you can see the differences between an RA and an ED foil and what the effects look like after we've gone through one, semming it, and then two, putting it through an etch for 30 seconds. You can see how we're attacking the grain boundaries. And that's just how etches work. There's a lot of stress in the grain boundaries, and etchants like to attack those areas first. It's where the copper likes to get released into the solution. So I'm a little bit over, so we're going to hopefully speed through some of our Flex specialty products here. So like I mentioned earlier, we normally do a limited cut, not bikini cut. And what we can do with our specialty materials is actually extend them through the rigid zones because they're stable and they don't have that low T to G I was talking about 40 C with acrylic adhesives. In this case, it's Pyrolex HT. It stands for high temperature. It has an MOT of about 200 degrees C. So if you need to do anything under hood, inside of a rocket casing for anybody up here, or any other kind of extreme thermal event, Pyrolex HT is going to be the flexible adhesive you want. It's got better electrical characteristics, and again, it's more chemically stable and thermally stable than standard acrylics. We also have a product called Pyrolex TK. It's a Teflon or a FEP coated polyimide material, and if you've ever worked with fluoropolymers, you understand that the orbital structures of those composites don't like electrons, which is great for designers because we can use that to get good electrical characteristics. And what you can see here is a cross section, SEM scan. You can see the differences in how we put that, where we put that FEP with the polyimide. And then the top right hand side here, you can see a TK flexible clad laminate and its insertion loss values. We also have an epoxy-based flexible adhesive called HP. It again, very good performance properties, but it's easier to process than HT. We won't get into that, but again, it also has very good electrical characteristics. So it enables some really intense design. So if you're doing anything at 77 gigahertz, you're going to want to use TK or HP, and HP is more process friendly. With that, are there any questions? Comments? Thank you so much for your time.